Which one? You can't just like randomly put a test on the thing like.
It's the one we were doing yesterday.
It's that for you.
Got it. I'll try to find it.
So like. Do you have earbuds in?
Oh, sorry. It was in from the other class.
The one you sleep in? Do you put on like white
I
noise?
actually did my work and I was actually good at it.
Good job. Okay, so the force is acting on this one. So first of all, what way is this one gonna rotate?
Right, clockwise.
It's gonna go this way, yeah? So it's gonna rotate this way.
Yeah.
Okay. This force that's going down from this one should be twice the length of this force. Yeah?
I'm in trouble.
Okay. So this one should be twice the length. Now, some of you guys, when you did this, you put like FG or something like that. You got to differentiate. If they ever give you the masses, what you want to write is 2mg as the force instead of FG. You want to write what the forces are. Then you want to make this one like half as much, and this one is mg. Okay, now you got to think about the tension forces. If this one's going to be rotating, then the tension force on this guy needs to be longer than the tension force on this guy. I'm sorry, then this one has to be longer than this one, and it has to be less than this one, yeah?
Yes.
Okay, so I would make it a little more than half, and then, like, but not quite, like, all the way.
Not quite two.
And let's call this T1. And then on this one, this tension force needs to be less than this guy, and not the same as this one.
More than that one?
It would be a little less than that one.
Okay.
Right? Hold on. I don't think that matters as much. I think they'll give you credit. I think what they're really looking for is that this one's longer. Here. That this one's longer than that one, and that this one's longer than that one. And that these two are unequal. Okay. So far, so good? I think that's the part that a lot of you guys got credit for.
Yeah, that's the one I got credit on.
Okay, the equations of translational motion, Newton's second law for each of the blocks. So this is only asking about Newton's second law. So it's for each of the blocks. So for this block, remember that it's sum of the forces equals mass times acceleration, and then you have sum of the forces equals mass times acceleration, where you start from there. This block is going to be 2mg minus T2 equals 2ma. So the sum of the forces, this one minus this one, where I'm calling the direction of motion positive. So, go like that. This block, wow, I should have written them on the opposite sides. That was dumb. Hold on. I do not have what's it called? Yes, I do somewhere, but I don't know where.
She said wider?
Yeah, I'm gonna switch the sides. I'm just gonna switch the sides because it'll make more sense to your brain.
Nani. I just wrote it.
Okay, and then this one, the positive force is T1 minus mg equals ma. Okay. That's all that question was asking you to do.
What are the plates?
Huh?
The plates.
I don't remember. I would have to look. Okay, so that's that. And then this one, it says write the analogous ones for the rotation part of it. So now here, what you're looking at is what forces are actually causing the rotation. So what you have is the sum of the torques, right? So that's the sum of the torques equals I alpha. Okay, and it gives you the I. Yeah. Okay, so from here, there's the tension force called T2, which is going opposite the direction of motion, and then T1, which is going in the direction of motion. So it's going to be T1R minus T2R is equal to 1.5, which is like 3/2 mr squared times alpha. So R times T1 minus T2 equals 3/2 mr squared alpha. So you can cancel an R off and get T1 minus T2 equals 3/2 mr alpha. Okay. I'm pretty sure if you just had this, they'd give you credit, but that's simplified. Okay, so now we want to solve the equations in part B to find the linear acceleration of the system. Okay, so when we have this, we have T1 minus T2 equals 3/2 mr, the moment of inertia of this pulley, okay, yeah, that's right. Okay, mr alpha is A over R, right? Is that it?
Mhm.
Okay, so that cancels. Okay, so now we have this. Well, we also have these. So let's solve these two formulas for T1 and T2. Okay, so T1 is equal to MA plus MG. That's this one. And then this one, T2 is equal to, if we move that and move that, 2mg minus 2ma. So I took these ones and I solved them for T1 and T2. Now I could subtract them, because that's what this says on this side, right?
Yep.
Okay, so I'm gonna simplify this. T1 is equal to m a plus g. T2 is equal to 2m g minus a. Okay, so now I'm gonna subtract them. T1 is m. No, I'm gonna, yeah, well, it's gonna make it easier. If I leave them like this, mg minus, yeah. No, okay. Ma plus mg minus this one, 2mg minus 2ma. Okay, equals, on this side, 3/2 ma. Okay, so let's distribute this in and then combine like terms. So this is minus, this is plus, so it's gonna be ma plus 2ma and then plus mg minus 2mg. Okay, so that's what this side equals, and then if we simplify that, it's gonna be 3ma minus mg, yeah? Equals 3/2 ma. What can we do to the m's?
So-
Because they're in all the terms. Let's combine these two terms. So let's subtract this over. Well, then okay, it's fine. Subtract that over. So we have negative g equals, if we subtract 3 from this, we get negative 3/2 a.
Wouldn't the A's cancel?
No,
No.
I'm subtracting them.
Okay.
So it's 3a, so it's 3/2 a minus 3a. So 1.5 a minus 3a is negative 1.5, which makes those positive. So a is that. All of that's algebra, really. But the trick of that one was figuring out that if you have T1 minus T2 and you have an equation for T1 and T2, you can subtract the equations. That was the whole trick of that problem.
Okay.
Yeah,
So whenever it asks for acceleration, we use the alpha, right?
yeah,
And
yeah,
that's the A over R, right?
yeah. It's how you relate the two together.
Okay.
Okay, so then if we want to find T1, determine the tension attached to M1. Okay, so T1 is equal to MA plus MG. So that is M 2/3 G plus MG. So that would be what? 5/3 G. That's good?
Could we have done the same thing for T2? Or,
Yeah, you just use the T2 equation, then you plug in the A as well, and then,
okay.
because it's all accelerating at the same acceleration, the whole system is. Is that okay?
Mhm.
Okay. This one is asking about the normal forces, and one student is saying the normal force is equal to the weight of the stand and the pulley plus the two tension forces. The table counteracts all the downward forces, so it's all of this. This one says the normal force is equal to the two masses, the pulley and the stand, but the tension are not part of it because they don't touch the table. So the two masses do add to the weight of the system. The normal force would be this. So what is true is that it is B, because remember normal force is contact force. So it's how much weight is pushing on the table, and that's what's counterbalancing it. So tension's not included because tension are internal forces with the ropes, and they're not actually touching the table. Normal force has to be a force that's actually acting on the table, which is the weight, the total weight of the system. That's what this is. Normal force is a contact force. That's the whole idea with that. Normal force is contact. I realized that grading things on Google Classroom is really easy. I didn't know. Okay. Questions on that? Because I'm gonna still review some more about, what is it called? What am I trying to say? Who's absent today? Anyone? I'm going to review some more about rotation. Oh, I have a headache. Do you guys have questions specific to rotation?
Not really.
Or do you want me to just review?
Yeah.
And you guys are still good for a Thursday test?
Yeah.
Oh, it's Thursday, right?
Yes.
Is it going fast?
Yes. Yes.
Okay.
I'm playing it. Class.
No, unless you're not taking the AP exam,
It's in class though.
then you are.
Because we're not doing anything now. It's just reviewing for like the one so we can in class.
Okay. Are we ready?
We still review from other shit, but it's not great. Oh, and don't forget that we got the.
Okay, ready? So rotation in general. When you're thinking about rotation, you want to think about that the equations of all of regular motion are the same as the equations of rotation, just with different variables, but they're analogous. So I'm going to rewrite what they are. So in rotation and then translation. So when you have your equations of motion, which are x equals x naught plus v naught t plus 1/2 at squared, or v squared equals v naught squared plus 2a delta x, or v equals v naught plus at. Okay, so those are your equations of regular motion. They're the same. You just change out the variables. So theta equals theta naught plus omega naught t plus 1/2 alpha t squared. It's exactly the same, just with the other variables in it. This one, omega squared equals omega naught squared plus 2 alpha delta theta. And then this one, omega equals omega naught plus alpha alpha t. Okay, so what you want to think about is translation means moving in space, moving across space. So like moving, like actually moving in space. Rotation just means spinning. So an object can be spinning without moving in space, or it can be spinning and moving in space. It can be doing both, or it can be doing just this and not that. It can be doing all the things. Yeah? So like a wheel, as a wheel is moving, I have a wheel. A wheel could be doing this, where it's just rotating. Okay, so that would be just all rotation. A wheel could be doing this. Yeah? Which is translation and rotation. Or a wheel could be sliding like that without rotating, right? So you would apply the equations that go with it. And what does the rotation part actually means? It means like, say that this is your point, this little thingamadoozer where you put air in, right? So if it's translating, if it's rolling, but it's also spinning, the rotation part has nothing to do with the moving this way. It's like literally how fast this little thingy is moving around the circle. So you got to separate out in your head rotation from translation. They're two separate things. How fast is a point on the edge of the circle actually moving around? That's rotation. Does that make sense? Mm-hmm. Okay. And then there's ways to go from one to the other. So ways that they're related. So velocity is equal to omega times r, and acceleration is equal to alpha times r. So these are the ways that you can go from one from rotating to translation, or translation to it's the way that they connect. Okay, so those are your kinematic equations. And then you have your sum of the forces equals 0, or sum of the forces equals ma. So remember that this is for equilibrium or for constant speed. And then this is for accelerated motion. Okay, so over here with these, you have your sum of the torques equals 0, or you have your sum of the torques equals I alpha. So the torque is kind of like the force, and then a moment of inertia is kind of like mass. Alpha is the angular component, or the angular type of acceleration. You have a third equation though. Torque is equal to F perpendicular to R. So this equation helps you get what goes on the torque side. Force doesn't have like an extra equation like this, but if you think about force has a ton of extra equations, right? Like you could say Fg is equal to mg. That's a force equation, like the torque equation. Or you could say the force due to friction is mu Fn. That's another force equation. There's a lot of force equations, but does that make sense? Mm-hmm. So like what you put on this side depends on what kinds of forces they are. What you put on this side depends on what the torque is. And torque has to be perpendicular to the direction of motion. So far, so good? Are you okay? Okay. Then we have energy. So we have our potential energy has nothing to do with rotation. Okay, so that's just going to be on this side. Now it can give you energy to put into rotation, but it doesn't, there's no like rotational component of potential. You have your spring potential. That again, anything that's potential energy has nothing to do with like rotation kind of stuff. But you have your kinetic energy, your translational kinetic energy, which is 1/2 mv squared, and then your rotational kinetic energy, which is 1/2 I omega squared. What you want to remember in conservation, over here if you're conserving, it's usually like this at the top equals the kinetic at the bottom or whatever. Mm-hmm. Over here, if it's something over here, it'd be at the top equals the kinetic at the bottom for rotation and the kinetic at the bottom for translation. You get an extra term on this side when you're in the rotation aspect. So if something is rolling down a plane, then you have the rolling, some of the energy goes into the actual motion. So this is why things that are rolling take longer to go down planes than things that are sliding. Things that are sliding without friction don't have to convert any of the energy into rotation. It all goes into translation, so it goes faster. And then you have your equations for I. Your generic equation for moment of inertia is mr squared. And this works for a point mass. And then you have your other equations for I dependent on shape, which they'll usually tell you. So if it's a sphere, if it's a hollow, whatever that stuff is. And that's what you plug into your I there, whatever the thing is. Then you have your momentum, P is equal to mv, and your angular component is L is equal to I omega. And these quantities are always conserved. Always. Energy is not always conserved. Sometimes energy is lost, but momentum is always conserved. If you plug into this L equation, your I of mr squared, and then your omega, which is velocity over r, you end up with mvr, which is very similar to that. It's just with an extra r. Okay, so those are really all. Is those all the equations? Yeah. Okay. Yeah, constant. Yeah. Okay, so those are all your equations for rotation and translation. So as long as you know how to do translational stuff, really you can do rotational stuff as well. It's not any different. It's just applying it to a different context. I think what we do is we tend to, like, we have this like story in our head that rotation is hard, and so it's like, oh, I don't know what to do because it's hard. But like, really, you know what to do. If it was something just moving, moving in linear space, you would know what to do. And then all of a sudden it's rotating, you're like, oh, I don't know what to do. You do. So just take on that you actually do know what to do. I promise. You do. You can do it. Okay, so things that you guys should know how to do. If you have a board or a thing, remember that the weight of the board acts at center point. Unless it tells you it goes someplace else, like unless it tells you that the board is off center. So if you have this board, you'll always have your force due to gravity of the weight of the board in the direct center of the board. Okay, and now if you put, if they tell you this is a meter stick, then this would be located at 50 centimeters. Mm-hmm. And then remember that when you're doing torque is F perpendicular to R, but R is distance from axis of rotation. So if they were to say like this is a meter stick and you put a mass at 20 centimeters, so here's the mass that you're putting at 20 centimeters, that means 20 centimeters from here, which means from here it's actually what? It's actually 30 centimeters from the axis of rotation. Okay, so wherever it tells you, like if it's a meter stick, and they like to do that because it makes you actually think, like if it tells you the points where they're putting things, you always want to think, okay, well if that's where it's at, then how far is it from the axis of rotation? And those are the numbers that you actually plug into your sum of torques. Yeah? Is that okay?
Yeah.
If it says that it's in equilibrium, then that means that you sum the torques equal to 0, which means that you pick a direction of rotation as positive. So you just pick a direction. I usually do clockwise as positive. And then what you would do, so let's say we have another one on this side, M2G, and let's say that this is like 20 centimeters away from here. And let's put the pivot point right on the middle so that I can get rid of the force right there. And we want to figure out like, what is M2 compared to M1 or whatever. Okay, so if this was our situation, what we would do if they knew this was an equilibrium, you'd sum the torques equal to 0, and then what you would look at is this one, M2G times its distance, 0.2, minus this one, M1G times its distance, equals 0. And then from there you can figure out like the ratio of M1 to M2 or whatever it's asking. If they might give you M2, then you have to solve for M1 or whatever. But does this make sense how you do these?
Yeah.
Okay. Now if you have two forces on one side, you then you'd have maybe two positive and one negative or whatever the situation is, just whatever way it's rotating. And if you had a force that was actually acting on the stick going this way, even though it's on this side, that's a positive force because it's causing it to rotate in the direction of motion that you cause positive. Yeah? So you gotta, like, what you wanna think about is like, okay, if I had a string and I was pulling this way, what way would it rotate? If I had a string, what way would it rotate? If I had a string, what way would it rotate? That's how I think of torques, is like pulling on it and seeing, like, in my head, okay, what way would it go if I pulled on it? Does that make sense? Yeah? Okay. Okay, so, yeah, things rotating, okay. Turn to, remember that angular acceleration? So that equation that is like omega equals omega naught plus alpha t, you can rewrite that as alpha is equal to omega minus omega naught over t, which this is the common way that if you probably remember acceleration. Yeah? Change in velocity over change in time.
Yeah.
Okay, so if you knew that something started from rest, like let's say you needed to know this. Okay, your alpha. Let's say something starts from rest and it rotates through one revolution. No, let's say that, okay, so the other equation too that you have is omega is equal to theta minus theta naught over t. Yeah? You know that one? So what if something is moving at a constant, this is velocity is equal to x minus x naught over t.
Jeez.
You know your regular, yeah? Okay, so what if something's moving at a constant velocity and it moves, let's say, 3 times around a circle. Okay, so something moves 3 times around a circle in time t. Okay, and I want to know what the velocity is. So omega would be, if you think of these, this, if it starts at 0, what's 3 times around a circle in terms of theta? How many pi?
270 or 2?
How many pi? Not degrees. How many pi? It'd be 6 pi. It'd be 6 pi, right?
Yeah.
6 pi over t. That'd be your omega. Now what if I wanted to know what the velocity was? It'd be 6 pi r over t. Yeah? Because the only difference is the r. What if it started from rest and I want to know, and it has a constant acceleration, so it starts from rest and has constant alpha, and I want to know what omega is going to be after 1 revolution. No, let's say 3 revolutions. Okay, so I would go to this one, starts from rest, so alpha is equal to omega, starts from rest is 0, over period time t. So let's say it makes so omega would just be alpha t. Now what if I can't have t? What if I can't have t? Is there another equation that I could use that relates alpha and omega? Alpha and, yeah, that's right, alpha and omega. without T in it?
T equals?
Oh, I remember this.
This one, yeah?
Yeah.
Okay, so if it starts from us, this is 0. If it goes 3 times around, what's this? 6 pi. So I would have omega squared is equal to 2 alpha times 6 pi. So that would be what? 12 alpha pi, 12 pi alpha. I like that way better. Okay, so what would be omega then?
Square root of 12 pi alpha.
Do you guys get what I'm doing there?
Mm.
Don't let the Greek letters make you nervous.
Greek letters.
Okay. What would be good? Are we following me? Tracking? Okay. What if I have a stick? Okay, a rod of some kind. And it's going to rotate about the center. And I put a point mass on this side. Let's say I want to know what the the moment of inertia of this would be. What would I have to do?
Find the distance of the whole thing?
Combine what? Of what? Of the what?
The system.
Of what part? What's in the system?
The ball and the thing?
The ball and the rod. Okay, good. So the ball and the rod. So I would have to do the moment of inertia of the rod plus the moment of inertia of the point mass. I'm going to put PM as point mass. Is that okay? It doesn't mean nighttime. Okay, so this one, you know, they would have to give it to you, or you'd have to remember what it was or whatever, right? Because I don't remember what it is. I don't know if it's 112. I think it's 112 ml squared, whatever. What would this one be? So this guy is mr squared. Now if this is length L, then what would R be? L over 2. So it'd be m L over 2 squared, which is okay, so that would be the piece that's from this, and then plus that, whatever that is.
Wait, why is it?
Because the entire rod is conserved.
Oh, we're just looking at the point, right? Okay.
And it's always from
Oh,
axis
radius.
of rotation.
Radius.
Okay, so if we're thinking about, let's talk about like the toilet paper roll. Here's your toilet paper roll, distance R. Let's just call it a sphere or a cylinder instead of a toilet paper roll, because I don't want to deal with the hard eye.
Did your head hurt?
I have my really bad.
I have
I'm fine.
Tylenol.
I just took 600 milligrams of ibuprofen. We'll see if it works. Okay, so let's call this T. Okay, what are the forces that are acting on this in terms of translation? If we drew a free body diagram.
So tension up. Tension up.
This is from the center of mass.
No, but where's the apparatus?
Oh, this is in equilibrium. Translationally. Meaning that it's not moving up or down. But it is rotating. I'm holding this, this is like toilet paper, and I'm holding the piece. So like, rather than holding my hand stationary and it falls, I'm lifting this so that
Oh, it just
this
bends.
is just rotating in free space.
Okay.
Yeah? Okay.
Wait, how are you pulling it?
And I'm pulling it, I'm with a force of tension such that it's in translational equilibrium.
Okay, so
Wow.
T is on.
So, what are the forces acting on this?
Tension.
Tension and those should be the same length, because they're in translational equilibrium. Okay? So, if I sum this, it would equal what? 0 translationally.
Mm-hmm.
Okay, so that means that FG is equal to T here. Okay, so that gives us an equation for that, if we needed to. That would be like what? Mg is equal to T. Okay. Now, what about rotation? The sum of the torques, is that equal to 0?
No.
No, because this thing is spinning. So that's equal to I alpha. What are the torques acting on the system? Tension, acting at distance R is equal to, now if this is a cylinder, 1/2 mR squared times alpha, which is, okay, so I have TR is equal to, yeah?
Mm-hmm.
1/2 MRA. And then, so T is equal to 1/2 MA. Which that's equal to
F of G.
mg.
Oh, yeah.
So G is equal to 1/2 A, or A is equal to 2G. That's fun, right? Was that fun?
Mm-hmm.
I enjoyed that. Did you enjoy that one?
Yeah.
Cool, yeah.
Why did we use MG?
Because of this.
You just said it equal to each other.
So what I did is I set up the translational thing to help me with the rotational thing. Yeah.
How can it be accelerating linearly to the station?
It's not. That's the acceleration of the hand,
Oh.
right? If you think about what in the system is actually accelerating, it's your hand. That's cool, yeah?
Yeah.
It's a fun one. Okay, so let's talk about a little bit about angular momentum.
Okay. It equals V over R?
So if you have the, here's your ice skater, yeah? Versus here's your ice skater. Okay, so here's your ice skater, arms in, arms out. So what we know is that arms out equals arms in. Yeah? The angular momentum of arms out is the same as angular momentum of arms in. Okay, because angular momentum is conserved. That means that the moment of inertia of out times the omega of out equals the moment of inertia of in times the omega of in. So this tells you that if you decrease the moment of inertia, so T out is bigger than T in. How do I know that?
Because of the line.
Because there's masses or their arms are out, right? So their moment of inertia is actually bigger. Because when your arms are in, you decrease your moment of inertia.
Yeah.
Okay, so what does that mean about omega out versus omega in?
It's less than omega in.
Yeah, they're inversely proportional. So this is why, like, you can think of the person standing there, right? And then as you decrease the moment of inertia, they spin faster. That works on everything. That works on anything that's moving. If you take something that's sitting far away from the center of rotation and move it close to the center of rotation, the angular speed will go up because it's conserving the angular momentum. This works for the planets, like the planet going around, right? If it's further away, it's traveling slower. If it's closer, it's traveling faster. Angular momentum is conserved. Is that okay? Yeah? Okay. Okay. If something, there's a question on it that's kind of challenging in terms of like thinking about what happens. So if something is falling but also rotating,
Whoa.
okay, so it's like as it goes down, okay? If you were to track like both of the positions of the balls as they move down, it would be going it would be moving downward, but it would also be moving like up and downward. Does that make sense? Okay, I'm trying to, okay. So something is rotating, okay, but it's also going like this, right?
Okay.
So if you think about this part of the ball, it's going down, up, just one ball, not two balls. There's two balls connected by a stick like this, okay? Stick, okay. So if you think one ball, this ball up here, it's falling downward, but it's also rotating, right? So it's if you're just thinking of like looking at the ball in your head, it's going like this. In terms of position, it's going like this.
Yeah.
Yeah? So if you were to graph that, your graph would go downward, right? So the trend would go downward, but it would actually go up and down, up and down, up and down, up and down, up and down. Yeah?
But the down has more emphasis.
Which means that makes a what? Yeah, it actually makes a sine wave. So if something is falling, that's rotating as it's going down, and you're tracking one of the things, the graph will, how would you find the linear, like the, whatever, how would you find anything linear from a graph that's going like this?
Find.
Best.
It'd be not necessarily best fit, it would be the line that's going through the center of it, yeah?
Yeah.
It'd be like what the center of mass of the object is doing. If I wanted to know something about something that's spinning, I'd want to know what is the center of mass of the thing doing. Because the center of mass of the thing, if this is rotating,
The center is just.
the center of mass is staying in this, it's just falling. It doesn't matter what the end points of the thing are doing because the center of mass is just moving translationally. Right? It's not rotating. The center of mass is not rotating. So if you were to graph it and you had this graph, you would be able to look at what the center of the graph is doing. And then that would actually tell you what's happening translationally. Does that make sense?
Mm-hmm.
It's like a weird thing to think about, but okay. Yeah. All right. Now, if something is sliding down a ramp versus rolling down a ramp, which one gets to the bottom first? Sliding, because what?
There's more energy.
All of the energy
In the translation.
is translational. None of the energy has to be wasted, or used as rotation, yeah? Okay. And what are the things that are always conserved?
Angular momentum.
Angular momentum and, yep.
Angular momentum and what?
Linear momentum.
I know momentum is always conserved, but I didn't know what she said. Oh my god.
Oh, this is fun. If I were to make a triangle, this is the origin, and here's a particle that's up here, a distance x away from the origin and a distance y
Center mass.
away from this, and here's my object, and it's moving this way. So this mass
What
is
is going
moving
on
this
here?
way. Okay, so here's my object.
Okay.
It's on an xy coordinate system. It's x and y away from the origin. And I want to know what the angular momentum is as it's going towards. What's the actual distance I have to find?
Why divided
I hate how
So
she
if
makes
it's
the
L
ones.
is equal to mvr, right? This r is this distance. Yeah?
Yeah.
How do you find that distance? You can use Pythagorean theorem, or you could use a sine or a cosine if you need the angle, right? So you might want to know some trigonometry. is all I'm
Cosine
saying.
functions off.
Heck no.
Sine error.
You do want to understand, I'm just going to say a little bit of oscillation. You know how there's always questions from other things?
Yeah.
The question from the other things that I put on this test happens to be about, one of them is about oscillations. So how is energy conserved in an oscillation if it's like with the spring, right? At the farthest, so if this is x is equal to 0, what is true here?
Kinetic energy.
Yep, potential is 0 and kinetic is at max. At its end points, velocity is 0, so kinetic is 0, and the potential is at a max.
Acceleration.
And the acceleration is at a
And
max,
the force.
and the force is at a max,
And the distance.
and the yeah.
Jesus Christ.
And all the other ones, the analogous are 0. You want to know how that goes back and forth, and you can set equal the kinetic energy to the potential here. Stop packing up, damn it. I have minutes left. The other thing is, what is work done? What is work done on anything moving in a circle?
Force times.
0.
Oh, 0.
Why?
Because it's perpendicular.
Yep, it's perpendicular.
Oh.
Your FERCs, your FRQs, guys, there's 2 on this one. They're 2 short ones.
Two. Okay, I like that. I like that.
One of them is more of an like you have to analyze some student's experiment. And then the other one, I feel like you should be able to get the other one. It's a paragraph length response, but it's really just that concept of conservation of energy in terms of translation versus rotation. So if you guys understand that, you should be okay.
Conservation of energy.
Conservation of energy
Translation.
and rotation. I'm not going to review this tomorrow. I'm going to review electricity tomorrow. And then Thursday we'll take a test, and then Friday I'll review something else. Cool.